This
Did back
is
up one,
the,
dude?
say again?
I backed up one.
Okay. All right, this is Rick Montel, Kilo Whiskey 4 Mike, Quebec. This is part 2 of chapter 3 for the technician ham radio license. We had another snafu. The first part of the class Wednesday night did not get recorded, so we're doing a re-recording so that we can have complete posting up on the internet. So let's get started. Protective components. Protective components such as fuses and circuit breakers are used to prevent equipment damage or safety hazards such as fire or electrical shock. And designed to remove power in case of a circuit overload. Fuses blow. It's a one-time protection. When it blows, you get another one. Circuit breakers trip. They can be reset and reused. They cost more initially to buy, but they tend to be cheaper in the long run. Fuses interrupt current overloads by melting a short length of metal. When the metal melts, the current path is broken and power is removed from the circuit. And that's a literal description. There is a little strip of metal that's inside the fuse. Small fuses, low current ratings. It can be, a wire slightly larger than human hair. On heavier duty currents, it's heavier metal, but it's sized so that the metal will melt when a certain current limit is reached, and that interrupts the circuit. All right, next. Replacing a fuse or circuit breaker with one with a higher current rating could allow the fault to permanently damage the equipment or start a fire. That's very true. Okay, schematic symbols. Fuses are the upper two. The one in the middle being the more common, the two circles with a kind of a zigzag line between them. And they will normally on the schematic give you a amp rating for the fuse as well, right on the schematic. Circuit breaker is the lower one. Here's some pictures of some fuses. The three in the upper ones are an older style automotive fuse, or some bench equipment, some stereo equipment, and so on would also use that style of fuse. The lower ones are definitely the more common modern fuses for automotive use. Circuit breaker. This is a 15 amp circuit breaker from your typical power panel like would be in your house or maybe in a business power panel. And that's rated for a maximum 15 amps. Above that, and it will trip. The circuit breaker that you're seeing in the bottom right, they call it a ground fault circuit interrupter, GFCI. And what that does is it measures the current that's going out to the circuit and compares that to the current that is coming back. And if there is a certain difference, and we're talking like it varies, but 10 to 30 milliamp difference, which, if you're talking a 15 amp circuit, 30 milliamps is not very much at all. It's like 1/1000th of the total current going out. If it's off by that much, then it assumes that that electricity is going somewhere it shouldn't be, maybe through somebody's body, maybe a short somewhere, but as soon as it detects that difference, it trips. It will open the circuit. And the test button you see down on the lower part there, that simulates that drain going where it's not supposed to. What happens there, you push the test button and it trips the breaker. And if it does trip, then that's telling you that the detection circuit is working. So, and you'll find those typically for outlets that are outside or in the bathroom, or locations where damp water damage, or not water damage, but water contact, I should say, is more likely to happen. And so to reduce the chances of somebody getting shocked, then you need a GFCI in the circuit. Okay, next. Let's do some practice questions. What electrical component is used to protect other circuit components from current overloads? And that would be a fuse. A. What is the purpose of a fuse in an electrical circuit? B. To remove power in case of an overload. Why should a 5-amp fuse never be replaced with a 20-amp fuse? Correct answer is C. Excessive current could cause a fire. Circuit gatekeepers, switches and relays. Switches and relays control current through a circuit by connecting and disconnecting paths for the current to follow. Switches and relays are described by their number of poles and the number of throws. A combination of poles and throws describes the switch. Each circuit controlled by the switch is a pole. Each position is called a throw. A switch is operated manually, while a relay is a switch controlled by an electromagnet. Okay, here's some examples of different switch configurations. The first one would be, it should be SPST. The T is in the wrong spot on that drawing, but it would be a single pole, single throw. You're controlling one circuit, and there is one connected position. So it can be on or off, but there's only one connected position. The second one down, single pole double throw. Again, you're controlling one pole, one circuit, but it has two different positions it could be in. This would give you a selection of between, say, light A and light B, or antenna A or antenna B. It's on in the upper position. If you move the arrow down to the lower circle, then it's on in the lower position. So that's a single pole, one connection, two possible circuits. Next one down, double pole, double throw. We're controlling two different circuits, and we have two different choices they can be in. The dashed line between the two bars, the two arrows, tells you that they are mechanically connected. When one is moved, the other one moves with it. And so you could have both of them in the upper position or both of them in the lower position, controlling two different circuits. The last one is a push button switch, and it's a momentary, well, typically they're momentary contact. This one is normally open. You push the button, the bar connects across the two circles and closes the circuit. When you release it, it opens back up. All right, next. Here's some examples of circuits, of switches. The one in the top left is a simple toggle switch. Over on the far right, we have a slide switch. The one in between them that's kind of upside down is a push button. The bottom left is a rotary switch, which can have a large number of selections or throws. And then the bottom one is a little, typically it's a programming switch type of deal. You use it to set programming for like a garage door opener or some of the computer controlled equipment. You can rock those switches. There's what, 10 of them there? Yeah. You can, there's 10 different switches that you can rock one way, you know, up or down, and open or close the contact, and that will, you know, program by your choices. You can program a certain item that, you know, where you pre-select like perhaps the frequency it operates on or the mode it operates on. But this is something that you pretty much set one and then forget it. So like a garage door opener, you program it to work with a given receiver, and then you close the little door and you're done. It's going to open that garage. Okay, next. Relays. I got that relay sitting here on my bench. Relays are mechanical switches that are controlled by an electromagnet. So you apply voltage to the control coil. That forms an electromagnet, which then pulls down on what they call the armature. It's a magnetic chunk of metal, and that physically moves the contacts of the switch. So you can control a relay from a long distance. You don't have to physically be there. You can have wires that run, you know, a long ways, and control that switch, that relay, by operating a remote switch. So you use a switch to control the relay. All right, next. Indicator meters and displays. Indicators and displays are important components for radio equipment. An indicator is either on or off. A meter provides information as a value in the form of numbers or on a numeric scale. A display combines the indicators, numbers, and labels. And a liquid crystal display, or we call them LCDs, is used on the front panel of many radios and test instruments. What is the function of a single pole double throw switch? Correct answer is C. A single circuit is switched between one of two circuits. So you can select, like I said, that's the one where you can choose antenna A, antenna B, light bulb A, light bulb B. All right, look at some schematics here. What type of switch is represented by component 3 in figure T2? That's going to be a single pole, single throw switch. There's one pole, and the only choice you have is on or off. So A. What is a relay? Best description of a relay is an electrically controlled switch. Which of the following displays an electrical quantity as a numeric value? That would be a meter. C. Here we have some schematic symbols. These are some of the more common ones. Okay, symbols are used when drawing a circuit because there are so many types of components. Yeah, tens of thousands. Schematic diagrams are a visual description of a circuit and its components that uses standardized drawings called circuit symbols. Schematics will show you how the components are connected electrically. What is the name of an electrical wiring diagram that uses standard component symbols? That would be C, a schematic. What is component 1 in figure T1? If you remember from class a week ago, that would be jagged line, sharp corners on it. That's a resistor, item A. What is component 2 in figure T1? Component 2 is a transistor. What is component 3 in figure T1? Component 3 is the symbol for a lamp, light bulb. Answer C. What is component 4 in figure T1? That would be the symbol for a battery, D. What is component 6 in figure T2? Component 6, that's the symbol for a capacitor. Answer B. What is component 8 in figure T2? Component 8 is a light emitting diode. Answer D. And if you see the multiple arrows that they have drawn on the diode showing that it is emitting the light. Okay, what is component 9? Component 9 is a variable resistor. Answer C. What is component 4 in figure T2? Component 4 is two inductors sharing a common magnetic field on a core, and that would be a transformer, item D. What is component 3 in figure T3? Component 3 is an inductor with the arrow on it that makes it a variable inductor. Answer D. What is component 4 in figure T3? That is the standard symbol for an antenna. Answer A. Which of the following is accurately represented in electrical schematics? The component connections. Doesn't show you where the parts are in relation to each other, but it does show you how they are electrically connected to each other. Answer C. Okay, radio circuits. An oscillator produces a steady signal at one frequency. It's used in both receivers and transmitters to determine the operating frequency. The process of combining data or voice signals with an RF signal is called modulation. Modulators add the data or voice signal to an RF signal or carrier. A demodulation circuit extracts the information from a modulated signal. So we modulate the signal when we're transmitting it out over the air, and then your receiver will demodulate the signal in order to get the information back that you're receiving. Mixers combine two RF signals and shift one of them to a third frequency, closely related to a modulator. What is the name of a circuit that generates a signal at a specific frequency? That's an oscillator, D. Which of the following describes combining speech with an RF carrier signal? Or combining it, that's modulation, C. Which of the following is used to convert a signal from one frequency to another? Answer is B, that's a mixer. All right, that's the end of Module 3. So, okay, I got it. And I'm going to have to click on this and accept it, I think. Nope, I guess not. Okay, I got a few demonstrations for you. Most of the demonstrations did get recorded Wednesday night. Just a couple things that did not get captured, so I'm going to redo those. What you're looking at here is a bench type power supply. It indicates the voltage on the left here, which is currently saying it's 2.04 volts. And it indicates the current on the right to 2 decimal places. And we're going to do a couple of demonstrations of Ohm's law. I have here a small 10 ohm resistor. It's rated for about 1/4 of a watt. If I apply 2 volts, ten ohms, I get basically 2/10 of an amp. That's about 400 milliwatts, or less than half a watt. But it's making this resistor get hot, applying that voltage across there. Not hot enough to start smoking, but hot enough I can't keep my fingers on it. Size on resistors is an indicator of how much power. Remember, we measure them in watts. How much power a resistor can handle. Here's a slightly larger resistor. It's 8 ohms. It's actually less resistance compared to the 10 ohm, but this one's rated for 20 watts. And the reason we care about wattage is because if I had taken that small one and hooked it up across 12 volts, it would have smoked. But I can take this one, and I'm going to crank the voltage up. Eight ohm resistor, 12 volts, getting 1.5 amps of current. So you take 1.5 times the 12, you're looking at 18 watts. And it's doing just fine. It's getting warm, but I'm not smoking it. If I hook that small one across this setting right now, I would smoke the small resistor. So size matters when it comes to resistors and their ability to handle wattage. And that's true of a lot of components. Now, I have here a lamp. This is actually an 1157 that comes out of the tail light on an automotive. Let me get this hooked up. Okay, there's 2 elements in this light. The first one is the one that's used for tail lights. The second one is the one that indicates your brake. Okay, that is the brake light. I'm sorry, that's the tail light light. It's dimmer. If I hook it up to the brake part, you can see it's brighter. So they got two different windings in this light. Here's your tail light. It pulls less wattage, less current. I'm pulling over 2 amps on the brake. Can't see to get the alligator clip connected. There we go. And I'm pulling 0.5 amp on the tail light. So again, the windings inside the bulb, the filament I should say, is a heavier duty filament on the brake portion because it pulls more power. It's a lighter, thinner filament on the tail light section. It's another case of where size indicates the power. Not the size of the bulb, but the size of the filament winding on the inside. Okay, and then the next part of this demonstration was the series and parallel circuits, and that part got recorded. So I'm going to stop now, and Howard can edit all this together. Okay, the filament in the light bulb is made out of a material that changes its resistance as it heats up. The hotter it is, the more resistance it has. So it doesn't directly fit Ohm's law calculations because as the temperature changes, the resistance changes, and you have to account for that. Okay, let's get a couple of bulbs put together in the circuit here. Pull my voltage out. Okay, the thing you want to keep in mind with the series circuit, the current is constant all the way through the circuit. Every electron that goes in comes out the other end. If you break the circuit, now are those showing up?
Yeah.
If you break the circuit anywhere, all current stops, both lights go out. I can put a simple slide switch in line with this circuit. And now I turn the switch on, turn the switch off, I have control. The switch is in series with the 2 bulbs. Turn them on, turn them off. Okay. Now, if you go back up here and you look at the amp meter, even though I'm feeding it 3.5 volts, I'm not getting the full current. And the reason is because each of these bulbs needs to use 3.5 volts of electricity because of Ohm's law. At normal operating temperature, this bulb would be 7 ohms, and I need to actually bring the voltage up to double because part of that voltage is being used by this bulb, the other voltage drop is being used by this bulb.
Okay, bring it up where we can see the bulbs.
See?
There you go.
So a little over 7.5 volts here. And I've got my half of an amp, but it took twice the voltage because half of the voltage is dropping on the first bulb. As it goes through the circuit, the rest of the voltage is dropping on the second bulb. Voltage drop, power consumed. Let's go back just a minute on these bulbs. If they are 3.6 volts and half an amp, what is the wattage rating on each bulb? I come up with 1.8 watts. And 1.8 watts is some heat, but it's quite tolerable. You're going to, there is a very relationship between the amount of heat produced and the wattage involved. And you always want to keep that in mind when you are dealing with components. The power supply that you're going to get for a radio needs to be able to provide the current and the voltage required for that radio because of the amount of power that the radio consumes. The bigger the radio, the more output it has, the bigger the power supply you're going to need. And typically, more power is physically a larger size. So if you take a power supply that puts out twice the watts, it's going to be a larger power supply. Okay, so the current is constant. It's half an amp in this circuit, anywhere in this circuit. If I break the circuit anywhere, it all goes out. That's the important thing to remember about series. Same electrons going in have to come out, and they're the same all the way through the circuit. All right, parallel circuit. Better turn this back down because I don't want to burn these bulbs out. Okay, I'm going to run my power supply back up to 3.6 volts. And if you notice, I'm pulling almost an amp on these. I have two bulbs in parallel with each other. The switch is still in the circuit. I can turn them both on, both off. That hasn't changed. But what has changed here is I'm feeding the rated voltage for each bulb, 3.6 volts. Part of that current is flowing in one bulb. Part of that current is flowing in the other bulb. They're splitting the current. If I disconnect one bulb, it goes out, the other bulb remains lit, and look at my current flow. It went down. If I add the second bulb back in, now I'm pulling twice the current. The voltage hasn't changed, but the current has. Because the current has, there's two different routes it can take, bulb A or bulb B. And at the 3.6 volts, each bulb requires about half an amp. So it doesn't matter which one I disconnect. When I take a bulb out of the circuit, its current is no longer counted, and the current required cuts in half. All right, so the two bulbs are in parallel with each other. The switch is in series with the bulb. If I turn the switch off, I break the whole circuit. No electrons travel. The current goes to zero, the bulbs go out. So the switch is in series with the two bulbs. The bulbs are in parallel with each other. Okay, any questions on parallel versus series? Okay. Okay, I got two switches here. Can you see that?
Yeah.
Okay. These two switches are in series with each other. What has to happen in order for this circuit to be complete? Somebody want to guess?
Complete both those.
Right. They both have to be closed in order to complete the circuit. And down here, I have two switches in parallel. What's the requirement here if I wish to complete the circuit? Somebody want to guess?
Depending on which switch that you close would depend on which of your lines would get the power.
Well, if either switch is closed, I'm going to get a circuit.
Right.
So either or, either switch or even both switches, doesn't matter. If I close one of them or both of them, I complete a circuit. But in the first case, they both had to be closed in order to make a circuit. What would be an example of the first case of the two switches in series? Where would you might see something like that? Especially in ham radio. Well, one example that comes to mind really quick for me is safety switches on a cabinet with high voltage. The older style tube type radios, if there was a lot of high voltage involved inside a cabinet, they might put a safety switch on the door. So when you open the door, the switch opened. And when the switch opened, it removed power to the radio. That would keep you from getting electrocuted by having a panel open and somebody sticking their hand in there.
I'll give you another one. You
Go
have
for it.
a power switch to turn on your radio, and you have a transmit switch to turn on the transmission portion of the radio. They both have to be on to transmit.
Yeah, when you turn the first switch on, it enables the receiver portion, but you don't get the transmit portion until you turn the second one on.
I'll back you up one step more. Your circuit breaker in the garage is the first switch, and the switch on the wall that turns the light on and off is the second switch.
And if either one of those is off, the light's not lit.
Exactly.
So even if you turn on the wall switch, if the circuit breaker has tripped, you're not going to get a circuit. Okay, I got one device here. This is a relay. This is a small relay. you have a coil winding. This is the electromagnet coil here, powered off of these two pins. And when you feed power voltage into these two pins, this becomes an electromagnet and it pulls down on this moving part up here. And then mechanically, this part moving opens and closes. You can see these two sets of contacts here. So when you add power to the coil, this set of contacts will close, both of them. So you can have two wires running from here, 1,000 feet to wherever your control is. And when you activate that control, whether it's a switch or a thermostat or whatever, when you activate that, this closes, becomes an electromagnet, pulls this down, and then it closes contacts on this set of contacts here and powers whatever it is you want powered on this side. So a relay is a remotely operated switch. That's a relay. And this switch has two sets of contacts and they both get moved. You can see that or not. There's two chunks of plastic that stick out against the copper strips and push the contacts closed. So this is a double pole switch because there's two complete operating poles there pushing, and it's a single throw. It can either be open or closed. That's the only two choices you have. So it's a single throw, double pole. All right, any questions on that? Okay, I am going to take a couple of minutes. I need to move this camera and we're going to go on to the next part of this. Okay, what we're looking at here is called an oscilloscope. And what an oscilloscope displays is voltage over a period of time. Right now, this thing is sweeping from one side of the screen to the other. It takes 1 second to get from one side to the other. If we want to look at a voltage, in this case, I have a DC battery. They're all DC batteries. You notice this is 0 volts here. The line jumps up. That's 9 volts going into that. It deflects in the positive direction with positive voltage. If I turn the battery around, feed it negative voltage, it's going to deflect downward. So anything below center is a negative voltage. Anything above center is a positive voltage. If it's going back and forth, it'll be AC. So I'm going to speed up the speed of the trace. Now what we're looking at is the signal that goes above. Let me get clear of that. This goes above and below the line. This is 60 cycle AC. With DC, the voltage stays above center. With AC, it's going above and below center. This is 60 hertz, 60 cycles per second. What I'm looking at here is the output of a small transformer. Okay, we talked about using diodes to convert AC to DC. So remember, the diode conducts in one direction. So here is a diode in line. We're keeping the positive portion of the signal. You see that? Here, the bottom is going to get cut off when I go back to the diode. This is rectification. If you connect 4 diodes up in a certain sequence and way, then you can get what's referred to as full wave rectification. And what we do is we take the bottom part and invert it. So everything that was going below the line now goes back above the line anyway. So we invert the negative part of the signal, make it a positive signal. And if you notice, there's twice as many humps here if you go back and compare it with the AC signal, we've taken this lower part, flipped it over, and stuck it in between the existing positive. We've taken the negative, reversed the voltage on it. There's a way of doing that with the diodes so that you get, this is what's referred to as full wave rectification. And then what we can do, the humps are a little bit disturbing to a sensitive circuit, so we add a capacitor in line and we can reduce the humps. We keep it at a higher voltage because the capacitor absorbs the charge and then releases that charge back into the circuit during the low voltage portion. If we go to a larger capacitor, we pretty much have DC again. This is coming out of a transformer, and the capacitor is charging, and then as the voltage out of the transformer is dropping, the capacitor is maintaining the voltage level by doing a slight discharge. There are still humps there. They're just so small you're not noticing them.
That's pretty cool. I've never seen that explained like that.
So this is how we take AC, standard old 60 hertz AC. This is what it looks like believe it or not, your incandescent bulbs in your house, they're lighting up during this portion here. And then as the voltage goes to zero, the light is going out or dimming. And then it lights up again when the voltage reverses. And then it's going dim again or completely out, depending on how big the element is, how long it takes it to warm up and cool off. But that light is flickering 60 times, or actually 120 times a second, because it's flickering every time it goes down and then back up. Okay. So you don't see it because your eyes are too slow, but especially on fluorescent bulbs, they really are doing it. You can take a photocell and point it at the fluorescent bulb hooked up to a scope, and you can watch the signal on the photocell as that bulb turns on and off. Any questions on AC and DC and rectification?
So that's what all power supplies are doing?
Pardon?
Is that what power supplies are doing for us then?
Well, power supplies are converting the AC to DC. They are also changing the voltage from 120 volts down to typically 12 volts for your radio. So there's a lot more circuitry in there than just the diodes to do the rectification. And then there's additional circuitry in there that senses how much voltage is coming out of the power supply. And as you increase the load on that power supply, it will internally work to maintain that voltage. That's regulation. It's what they call voltage regulation. It maintains a constant voltage with a changing load.
I see. So this is just the rectification stage.
Right. This is just a rectification stage, which that's where you start. And then there's a whole different world of power supplies that's called switch mode.
However, they still have the rectification.
Say that again, Howard.
They still have the rectification.
Yes, they do. But the switch mode power supplies have a whole lot more circuitry in them. In fact, there's usually a couple of different stages. It'll do initial rectification, and then it has an oscillator in there that generates a high frequency signal that goes to a transformer. That comes out AC at a different voltage on the other side, and then that gets rectified into DC again. So there's multiple stages of rectification in a switch mode power supply. Okay.
So is this what we would think if we were using the radio?
Say that again, please.
I said, is this display, is this similar to what we would see if we were using the radio?
No. This
Okay.
device, what this device does, this oscilloscope, and I got another scope here. It's a similar scope. This displays voltage, how voltage varies over time. And because the voltage is varying so fast, in this case 60 cycles a second, we can't see that. You can't put a voltmeter on it and watch the voltage go up and down. The voltmeter cannot respond fast enough. If it's 60 times in a second, that it's doing a full up, down, and back up again. So the oscilloscope lets us see higher speed changes in voltage than what we could ever see with a voltmeter. That's the idea of an oscilloscope. And it displays that voltage change over time. So as that trace moves from the left to the right, you're seeing what the voltage is doing, going up and down over time. Okay, I'm going to come over here to another signal. Okay. What I have here is an oscillator. That's the lower. This is referred to as a signal generator or a function generator. This thing is capable of generating signals at various frequencies that are, that you select. It can generate the signal frequency and the strength, the amplitude of that signal. Okay, let's get. Okay, I'm going to set frequency 1 kilohertz. I'm going to slow down the speed of the scope. Okay. So what we're looking at here is a signal that's going up and down 1,000 times a second. And I can increase that. That's 10,000 times a second. So I got to make the scope travel faster across the screen in order to make it where we can understand what's happening. So this is happening 10,000 times a second. Okay, I'm going to put an inductor I have connected an inductor between my signal generator and my oscilloscope. And I can set this up so that it will change. I can walk the frequency down. There's 9,000, 8,000, 7,000. Okay. This is 3,000 cycles per second. As I step down, there's 1,000 cycles a second. The voltage, the apparent voltage, the amount of signal getting through to the scope, which is represented in the height. We're going to go up. There's 2, 3, 4, 5. As we go up, notice the strength of the signal gets weaker. This is an inductor. The slower the frequency, the less resistance it has. Remember me talking about AC reactance on an inductor? It's less at low frequencies. As you go up, the resistance increases, the reactance, technically AC resistance is reactance, increases. So it's harder to push a signal through an inductor as the frequency goes up. Okay? Same signal. Let me make the connection. Okay, going through a capacitor. If I walk the frequency down, notice the signal strength gets weaker as I go down. Go up in frequency, and the capacitor passes more of the signal through. Here's a direct connection, nothing in between them. There's the capacitor. As the frequency goes up, the capacitor passes more and more of the signal. So the resistance or reactance, AC resistance, is less on the capacitor as the signal frequency is higher. And on an inductor, it's the exact opposite. The amount of signal going through, the resistance on the inductor goes up with frequency because the windings in the coil react with each other as the frequency, as each cycle of the wave is going on, it is impeding the flow of the signal through the inductor. Now, real interesting thing happens when we start talking about putting the two of them in the circuit together. Okay, I have the inductor and the capacitor together in series, one behind the other. As the frequency goes up, I get less and less signal. Going up. Let's step this thing up a little faster here. I may have missed it. Coming down. Okay, signal gets stronger. As we go, okay, we're going down, now it's getting weaker. Let's go back up. There's 1,000, there's 2,000, 3,000, 4,000 is getting stronger, 5,000, 6,000, getting a lot stronger, 7,000, wait a second, we're at 8,000, it went down, 9,000, it's going down again. This is a band pass. There is a resonant frequency in the middle here, 7,000. That's where it passes the signal the best. If you go above that, it's not wanting to pass. You go below the 7,000, it's not wanting to pass. But there is a frequency where you get maximum signal through. This is a bandpass filter. Everything above and below is reduced. There's above, back to the peak, get below that, signal strength gets reduced again. So we're selecting this frequency, 7 kilohertz. That is what this filter will pass the best. Okay, I'm going to take a resistor and a capacitor. Now I've got them hooked up in parallel with each other. We got the exact opposite effect when they are in parallel. Signal is stronger at 2, 3, not quite as strong, 4, it's getting weaker, 5, 6, not much difference between 6 and 7. We go above, and it starts getting stronger again. So at frequencies above the resonant frequency, it's passing the signal. At resonant minimum pass, as we go down in frequency, it's passing again. This is a band rejection filter. It passes the ones higher and lower, but there is a frequency in the middle. And with this particular combination of capacitor and inductor, we're looking at around 7 well, in this case, it's more like somewhere between 6 and 7 with this particular set. Increase or decrease the value of 1, and that frequency point will change. So that's resonance. It is a frequency where the inductance from the capacitor and the inductance from the inductor, the reactance from the capacitor and the reactance from the inductor cancel each other out. Okay. Any questions? I put everyone to sleep.
And I guess it makes no difference which comes first when they're in series, about
Correct.
how it behaves.
Correct. And obviously, when they're in parallel with each other, there is no such thing as one coming before the other. It's at the same time. And everyone has this reactance down. Does reactance go up or down with frequency on a capacitor? If you increase the frequency, what happens to the reactance on a capacitor?
Goes down.
Goes down. Capacitors carry high frequency. They'll pass high frequency better. They do not pass low frequency as well. And inductors are exactly the opposite. An inductor will carry DC. You cannot get a capacitor to carry DC. Okay. I got one more circuit I want to show you guys. Let me get this hooked up. And I got to bring the camera over here just a second. Can you guys see the LED?
Oh, yes.
All right. Should be a blue LED lit. Can you see it?
Mhm.
Now, I got positive connected here, goes through a resistor into an FET transistor. Comes out of the FET and goes through the LED, goes to ground. This is how sensitive the gate is. This yellow wire here is connected to the gate on the FET. I told you on an FET, all it takes is a voltage being present, just an electrical charge. If I touch the positive and touch the gate wire, it turns the LED on. Okay. The neat trick is, once the charge has been established on the gate, it stays there. Doesn't need a current. It's just a voltage. If I want to turn it off, I ground myself. When I'm grounded, turns it off. But it's so sensitive that I can turn it on just the electrons in my body. But by touching the positive side over here, I'm getting enough more electrons that I can turn it on. Stay on you. There we go. That's how sensitive an FET is. You can't even measure the current required. It is just presence of voltage. Ground myself, turn it back off. Any questions on that? You guys are making this awfully easy. Okay. I've got two big numbers I'm going to throw at you. Let me turn the computer around, and we're going to do a couple of things talking about a new word for you called a column and what it really means. All right, let me do this. Okay, so Howard, do you have it set up where I can share the screen?
Yes.
Okay.
You are the host, so you can share your screen.
All right. Then let me see if I can find the file. Should have shown up there. Share screen. It's not giving me the choice of the files that I'm looking for. All right, well, we'll do this the other way. All right, I'm going to give you two numbers. The first number is a 6, 2, 4, and then 15 zeros. I'm sorry, 16 zeros. 6, 2, 4, 0, and then 15 zeros after that. So it's a 19-digit number, starts with 6, 2, 4. That number is one coulomb. C-O-U-L-O-M-B. It's a big number. That number represents the number of electrons that flows past a point at 1 amp. So when you have 1 amp of current flow, that many electrons are flowing past a point in the wire in 1 second. That's 1 amp. That's a lot of electrons. Here's a second large number. 7 comma, 500, and then 15 more zeros. That's also a 19-digit number. And there's a little story behind that number. Two scientists were discussing the question, is there more grains of sand on planet Earth or more stars in the heavens? And so they sat down and did calculations, and somehow they came up, I don't know the math they used to get there, but they came up with the second number. 7,500, and then 15 more zeros. The second number, the number of grains of sand on planet Earth, is just slightly larger than the first number I gave you, 1 coulomb. So imagine a pipe, and you're going to pass every grain of sand on planet Earth through that pipe in 1 second. That's 1 amp of flow. A lot of electrons. Now, when I told somebody else about that first number, I said, do you have any idea what that is? You older folks might get this. They said, yeah, that's how much money Imelda Marcos spent on shoes. All right.
That was in just one trip to the store.
She had a lot of shoes, I'll tell you. And I don't know why she's been back in the news lately, but I've seen a couple of different things pop up with her name in it. So I'm not sure what's going on there. That pretty much is going to cover my discussion on electronics. I probably will come up with a couple of more demos, just like 10-minute sessions after somebody else is done teaching. Just some more things I want to try and get across. Threw a lot at you tonight in one night, so I think, you know, the human mind can only accept so much information in a limited time like this. You get beyond that and it just becomes mud. So are there any other questions about what we have covered tonight?
I don't have.
Well,
any
I think we're going to
questions.
get out of class a little bit early tonight.
Mike had a question.
I said I don't have any questions, but I do want to thank you for the informative teaching that you did.
Any feedback on the demonstrations? Anything that wasn't as clear as maybe you wanted? Something I didn't cover you wanted me to cover? Okay.
Well, yeah, I'd agree that the visual demonstration of the rectification was pretty cool. Probably the first time I really understood that.
Okay. Yeah, the two types of scopes I have there. The first one is what they call a analog scope. And what you're seeing there is real time. The electron beam that's moving across the screen is deflected in real time by whatever voltage is being applied to the plates. The second scope that you were seeing is referred to as a digital storage oscilloscope. And there is a microprocessor involved. It sees what is happening to the voltages over time, does some calculations, and then puts the information up on the screen and displays it. So it's not real time. There is a slight time lag between the two. But the difference is with the digital storage oscilloscope, I can have a very fast short waveform that occurs, you know, momentarily. The scope can catch that, store it, and then show me on the display what happened. And I can stretch that out and, you know, look at different parameters on it. With the analog scope, it happens in real time. And if you didn't see it when it happened on the scope, you're not going to get to see it again. So they both have their advantages. And that's part of why I have both. The analog scopes were the original ones. The digital storage scopes came along later as we got more sophisticated equipment, microprocessors, the storage, memory and stuff that could make that work.
I saw that analog was a Heath kit. You didn't build that, did you?
Yeah, I did back in the mid 80s. That scope is approaching 40 years old. And that's actually my second scope. I built my first oscilloscope that was also a Heath kit back in the early 70s. But it isn't near the oscilloscope that this one is. This oscilloscope that I have now for my Heath kit is it's a capable enough scope that it's still relevant in today's world. So, all right, anything else? All right, I'm going to say good night to everyone. Like I said, we're getting out a little bit early, but and I will try to get some more demonstrations available as we go along in class. But they're just going to be short little blips, at the end of a teaching session.
Yeah.